Okay, welcome to the first afternoon session, to the Ionosphere and atmospheric session. We have started a little bit late because of delays with the lunch. And yeah, welcome everybody. And so my name is Falk Amelung. My co-chair is Giovanni Nico.
Yeah.
And yeah, okay, where are my glasses? You can see it.
Maybe I can read for you. The first presenter is Felipe Betancourt Pavan, who is going to present a work. The title is Towards an Interferometric Autofocus for Ionospheric Phase Signatures in Biomass. You have 20 minutes, and 3 minutes before I will give you the time.
Thank you. Yeah, you hear me well? Yeah. So welcome to my presentation of today, which is like building the path towards the interferometric autofocus for the ionospheric signatures in biomass. I'm going to, wait, can I? Okay, now. So I'm going to speak about a bit about biomass and about the ionospheric errors. Then I'm going to describe a method for the calibration of the, a method for the characterization of calibration errors, and then I'm going to show some examples with the Faraday rotation and the autofocus. Then later, I'm going to also describe a new method to kind of combine the solutions that I get from calibrating the single-pass products with interferometric products and try to gain a bit of resolution. And at the end, I'm going to just wrap up everything with a summary. So a bit about biomass. It's just going to be a new SAR mission that is going to be launched in 2025, and it's going to be the first time we're going to have a P-band, fully parametric system working from space. And then we're going to be working at very low frequencies, and the drawback then is that we are more affected by the ionosphere, so it will leave a signature in our images. The effects that we see in our products are the delay of the wavefronts that produce geolocation errors, phase cleansing the interferometric pairs, phase errors that introduce azimuth shifts and defocusing, and then dispersion, and then rotation of the polarization angle because of Faraday rotation. Just as a disclaimer, the ionosphere has a background and turbulent component. The background is changing slowly, and the turbulent is made up of electron density irregularities that change quickly, and we're interested in them because they are the ones that produce defocusing and scintillations. Regarding the assumptions that I'm going to use, so we know the ionosphere is like a volume, but the interesting electromagnetic interaction happens close to the height of maximum ionization. I am also going to assume that the background component of the ionosphere can be completely removed, and that's a reasonable assumption because we are sampling at a very high rate, so you can actually do lots of averaging. And the assumption that I'm actually interested in is that the spatial distribution of the irregularities change in a stochastic and stationary manner. That means that the spatial statistics of the ionospheric irregularities can be described, from spatial statistics, and speaking of the size, the shape, and the orientation of the irregularities, all that can be described by a power spectral density function that in our case, we're just going to go for the very famous 2D Reno power law for the phase delay. And since between phase, Faraday rotation, and tech, everything is linear, if I know the power spectral density of the phase, I also have the power spectral density of the Faraday rotation that I'm going to be using afterwards. And with this animation, I'm just want to introduce that the way that we're sampling with SAR, we are kind of like band limiting, sampling something that is not necessarily band limited. So these power spectral densities are not band limited, and that's going to be the first step towards our calibration studies. So just imagine that this is the power spectral density of the ionospheric irregularities. I've been thinking, I'm going to be discussing the azimuth direction because it's a bit more interesting, but in the range direction, the problem is pretty much the same. So in this green area, you have the azimuth bandwidth that is given by the beam, so it is what it is. But then you also sample at a bigger, like a bit higher rate, this PRF. So as I was saying before, we are sampling in the time domain something that is not necessarily band limited. So in the frequency domain, we are introducing these replicas that might enter into our calibration of observation bandwidth as aliasing. That will be these blue lines that you see over there. That red line is whatever noise that might enter into my observations. And in pink, what I did was pointing out the part of the ionospheric signal that I don't see it because it just falls outside of my calibration bandwidth. And like this, I can start coming up with an expression to try to estimate what will be the energy of my calibration error. That is going to be a sum of whatever happens inside and whatever happens outside of that green area. And just now here, the only thing that I want you to remember is that if I know the power spectral density of the signal, and I know, or I can keep track of all the responses of all the operations that happen during the calibration, I'm able to come with analytical solutions or analytical expressions for what I expect the performance of the calibration to be. And if everything is stationary, I can also say that the RMS, that is going to be the parameter I'm going to be using, the RMS of the calibration error is just the integral of all this power spectral density. And I forgot to say before is that all these parameters of the power spectral density, I can try to extract them either from models like the WB mode, or I can try also to extract them directly from the data, and there are methods for that. So the assumptions that I was commenting before are not necessarily too restrictive, because as long as what I'm seeing in my images has a structure, is more or less stationary, I'm going to be able to use the method that I'm going to describe. So now I'm going to also present what will be the calibration performance of the two L1 products by using the Faraday rotation and the autofocus. But before that, I'm going to just talk a bit about the simulation scenario. So I use the biomass end-to-end simulator and the processor prototype just to have like an accurate geometry and all the parameters of the mission. I chose somewhere close to the equator, not close to the pole, just because then I have very high resistivity to the Faraday rotation and the results look a bit nicer. So you have the tech, the Faraday rotation, the phase, and the phase. And since we don't have biomass data yet, I just decided to put everything into a TerraSAR reflectivity image just to test how the autofocus will work. Oh, yeah. Regarding the Faraday rotation, so you know that the radio waves go down and up, and it goes to the ionosphere 2 times, and every time it goes to the ionosphere, the polarization angle rotates a bit. And there are different ways to measure that rotation angle. The most efficient way is the Birkeland-Bates estimator that is limited by the signal-to-noise ratio, that if I assume that is more or less the same everywhere in the image, it translates in the frequency domain as just some kind of flat noise. So if you check the power spectral density of the Faraday rotation and where it cuts this noise floor, I can also design a filter that will cut just there, limiting my resolution at the maximum frequency that I can measure. So I don't let a lot of noise coming in, but I'm actually letting part of the signal coming out. And that is what you actually see up there in the error map, which is not just noise, it has a structure, and it's just the high frequency component of the Faraday rotation screen. And the RMS of that map is just the sum of whatever happens inside and outside of the band. So inside you have whatever noise, some aliasing that I usually will, I will neglect because it's very small, and the part of the signal that is just not visible because we are not calibrating it. And I did this for another thing, but I thought it was nice to show that in the polar cases, we expect with calibrating with the Faraday rotation to have some resolutions we go around a couple of kilometers, which I think is nice. Regarding the autofocus, the thing is a bit more complicated, so I'm going to try to go a bit step by step, and I hope that you can follow. So I'm going to be navigating between the picture, that's the figure that is like in the top left, sorry I can't point from this side, and the equation that is down left. So the autofocus works by blocks, and what it does is that locally it measures the amount of defocusing that is related to the second derivative of the phase variation along the azimuth direction. I try to zoom it in the middle picture because it's a bit of a weird second derivative. So the way the map does it is that calculates the second derivative of, the second derivative is kind of like the difference of the two slopes that are across the two halves of this syntactic aperture. That's the red and the green line. So there are probably other ways to do it, but for me what made sense was I took these three blue dots, and then I draw the slopes, and then I do the difference between them. And as you can see on the bottom right equation, so all that at the ends are linear operations that are not necessarily adding anything weird into my red component in the bottom left equation. This B is the block averaging that happens because of the block. This is the block averaging in the range direction. Since now I am sampling at a much lower rate, the aliasing is going to enter into my solution, so that's why I have to keep it in mind. And at this point, I'm going to have just like a map of second derivatives at the centers of the blocks that I will have to integrate 2 times. That's that integration part. And like this, I come to a downsampled version of the final solution that I'm looking for. Those are these blue stars that I have to upsample it again with a linear interpolator in order to be able to correct for everything in the images. Yeah. And like this, I'm able to come up with let's say, a solution for the performance that I can expect from the autofocus. So on the left will be like the analytical solution, the analytical performance, and on the right I have what I am able to recover with the autofocus as it is in the processor prototype at the moment. So you can see that the solutions are very similar, the error maps as well. The error still has a structure that is aligned with the regularities, which is fine. And but I can see it better in the power spectral densities, where I see that if you notice at the beginning, it seems that I have like a bit more energy in my solutions, and that happens because of the aliasing, and all these notches that go down like this are because of the linear interpolator that I'm using for upsampling, that is like multiplying the machine square in the frequency domain. And here I just have the input response of a couple of point targets in my image, so I can see that at least the mean lobe is a bit recovered, or is better recovered, yeah. So like this, I'm able to, let's say, come up with expressions for the performance of the single pass calibration. And then we see that there's going to be some residual phases and some residual errors left behind that are going to be able to see in the interferometric products. Then I have to calibrate them. Maybe there are methods for that. But I was thinking that given that the single pass solutions have lower resolution than the interferometric ones, but the interferometric solutions only give me differential information, I was thinking that there must be a way to connect both so I can obtain at the end better single pass solutions. And I thought that the way would be forcing the single pass solutions to, like, I calculate them separately, but I force them to be consistent to what I see in interferograms. And that's what I'm going to discuss now. So in biomass, we're going to pass like up to several times in the tomographic phase. So we have actually like a lot of passes and a lot of information we can combine. So let's say I take each of the individual passes, I calibrate them as we know, either with the Faraday rotation, the autofocus, or a combination of both. And then I will get some phase estimations with whatever error. Then later I do this interferometric calibration, and I get the differential phase with whatever error. And then I put everything together into some system that I expect that is able to cancel out all these inconsistencies and gain a bit of resolution. I went for a least square system because I know that it's able to combine different data sources, and also since at the end everything is linear, even in the interferometry you're just doing one minus the other, so then why not? But the thing is that at the end I'm going to be able, I expect to get like better solutions for the single pass solutions. And then now I'm just going to show, like in each column, there's some 1D simulations that I did. I think, let me check the colors. So in green you have some phase that I simulated. In blue, yeah, it's in blue, what I will recover by looking at the Faraday rotation, and in green, in orange, like what I will obtain if on top of that I also use the interferogram into my combined data. And maybe we can see it better that in the next, that if we have like a lot of data combined, so I'm having like I'm able to obtain better solutions. I can see that also better here, where I can see that the more passes I have, the more information I'm combining, the better the solution I'm going to get. And I need to confirm this, but I think all this looks to me like a 1 over n or 1 over square root of n passes, but I don't know, I have to check it out. For the autofocus, I'm also getting something very similar. So just notice that when I do like a lot of passes, I'm actually able to just cancel all these inconsistencies and gain actually quite a lot of resolution that I didn't have before. And also when I do the RMS of the error, I have more or less a similar result as before. Just looks a bit ugly because I think that the granularity of the autofocus error just affects my solution. Yeah, and just to finish up, so we have proven that with some spectral analysis, I can characterize the performance of the calibration methods. That is a good thing to have. But still, all these residual errors, we're going to be able to see them in the interferometric products, but we can also combine all the information together to gain some resolution and reduce uncertainties. And the approach goes by forcing the single products solution to be consistent with what we see in the interferograms. And also, like, the more information I have, the more information I combine, the better. So that was it. Thank you, and welcome with your question now.
Okay, thank you very much, Felipe. I'm sure there are some questions. No questions? There's, okay, sorry, yes.
Hi, Felipe, thank you. I just been trying to understand a little bit better. So you are taking the 7-image stack with the corrections which were calculated using multi-squint or split spectrum, and then you use that together with the autofocus screen, and you create some sort of combined screen that you then use to refocus the data.
Yeah, so what I'm trying to do is, I have the calibration of the single products from the one hand, and then I have the interferometric calibration on the other hand. But so then I have like two different kinds of solutions, and then I kind of put them everything together into one system. So like this, I'm able to get better solutions for the single pass products.
Yeah, no, because I see two things. One thing would be to improve really the results. The other thing is to actually provide the ionosphere estimation. No?
Yeah, I mean, yes, the ionospheric estimation, like the irregularity, you know what I mean.
Yeah, it's one of the biomass secondary objectives to provide some sort of tech maps.
Yes, and like this, I'm getting, because when you are calibrating, you need to get a reliable ionospheric screen that is an ionospheric product, so yeah.
Good, we discuss more later.
Okay, are there any other questions? If not, then, let's just continue. We are almost back to our schedule. So the next speaker is going to be Sausem Beladi Aisa, and from JPL, Pasadena, and he's going to talk about spaceborne INSAR versus airborne INSAR propaganda change.
Okay, got it.
She, sorry.
It's fine. Okay. Hello, everyone. My name is Sausem Beladi Aisa. I work as a postdoc at the Jet Propulsion Laboratory, and I have the honor to present on behalf of my colleague a summary of our work entitled Spaceborne INSAR and Airborne INSAR for Water Level Change Monitoring in Coastal Wetlands. Wetlands, where water meets land, they cover up to 8% of the Earth's surface. They are an important ecosystem. They ensure a bunch of services such as water purification, flood protection, carbon sequestration, and so on. Yet the world has lost up to 65% of its original wetlands. Thus, the importance of their hydrodynamic processes monitoring. So far, the observation of their hydrodynamics was achieved using a network of water gauge stations. They do provide measurement of water level change with fast temporal sampling, but they are spatially sparse. That's where SAR interferometry emerged as a valuable tool to characterize hydrodynamics on a larger scale. So at Jet Propulsion Laboratory and through the NASA Delta X project, we aim to generate hydrodynamics models using jointly in situ measurement and remote sensing measurement. We intend to do that on a local scale using airborne remote sensing and a larger scale through a global Delta project using spaceborne remote sensing. So for the airborne sensor, we use the Averis NG for spectrometry. and AirSWAT for surface water topography and slope, and UAVSAR L-band for interferometry measurement. Okay, interferometry in wetlands. It works thanks to the emergent vegetation, which with water create a double bounce back scattering. So after removing the topography component, the phase difference or the interferogram will be proportional to the water level change, and that's what we are looking for. Although in practice, INSAR processes is the same for INSAR, for airborne or spaceborne, but the challenges and the consideration faced are different. For instance, for the airborne INSAR, the main problem we faced was the atmospheric effect, but more specifically the wet troposphere. We're talking here about 12 to 15 kilometer each of altitude. So using the UAVSAR acquisition, we applied S-base as a time series analysis. We generated water level change maps. And however, we observed those maps are to be used to calibrate the hydrodynamics models. However, we observed on those maps some features that are not related to the water level change. We assume those features to be related to precipitation event or cumulus cloud, condensate cloud with water particle. So to solve this problem, we applied a signal processing technique known as an ACA, independent component analysis. So ACA is a data analysis technique. It's used to separate different signals of different sources mixed together. So we apply the ACA, we generate the independent sources or the different sources that are mixed within the time series, and we used in situ measurement to identify the source or the signal related to the water level change. Once we identify the source, we apply ACA inverse and we construct a filtered time series that's going to be used to calibrate the hydrodynamics model again. So we validated the results that we have against measurement, in situ measurement, showing here plots, temporal plots. So the blue line is the in situ measurement. The red line, the green lines are the temporal trend before the filtering, and the red one is after the filtering. As we can observe after the filtering, there is a better correlation between the water level change measured with the in situ, with the water station, the water gauge station, and that what we achieved after the ICA filtering. With the remaining component, disregard as atmospheric component, and image segmentation, sample image segmentation, we highlighted the atmospheric features, what we labeled as atmospheric features. And we validate them against NextRad. It's a ground-based weather radar using S-band. So we compare some of the masks that we generated through ICA, and we compare them with their reflectivity maps from the weather radar. We can observe a pretty good spatial matching, spatial correlation. So I guess we're doing a pretty good job here. Now regarding the spaceborne INSAR, there are other challenges faced, right? There are other problems that we always face while doing INSAR in different environments, especially vegetated environments, which is really tricky. But the main one that we faced was the coherence loss, the rapid coherence loss. So in the scope of Global Delta and as preparation for the upcoming mission NISAR, we used ALOS Pulsar 2 ScanSAR acquisition that we acquired through a project with the Japanese Spatial Agency. We used ICE2 as an interferometric tool to generate 9 interferograms covering the winter period by the end of 2018 and early 2019. So we observed on these interferograms, some of them show really good fringes located near smooth fringes, located near water channel representing water level change. However, we did observe also some of the interferograms showing discontinuity, fringe discontinuity due to coherence loss. There's also a correlation between the coherence loss and the type of wetlands. In fact, forested type of wetlands, they tend to have a better coherence than herbaceous type of wetlands because the woody trunk of the forest is more resistant to wind and atmospheric effect, so they tend to have a more stable and better coherence in time compared to the compared to the herbaceous type of wetlands. Oh, sorry about that. So in summary, as a takeaway, at JPL, we have, through NASA Delta X project, we are using remote sensing measurement to calibrate hydrodynamic models. Those acquisitions, specifically the UAV SAR acquisition, were affected by atmospheric delays. We did successfully identify those atmospheric effects and filtered them using independent component analysis. And we're aiming to do the same thing, but globally using spaceborne images, spaceborne remote sensing. We do have preliminary results that show they are promising, but I'm pretty sure we still have challenges, yes, to be faced and solved. For the time being, I think we're advancing pretty good. Thank you for your attention.
Okay, thank you very much. I'm sure there are questions. No questions? I do have a question. How many of those UAV SAR images did you have?
Oh, so we had 16 flights, and the images we used for this data set specifically, there were seven images.
And what was the temporal baseline of those?
20 minutes, between 20 to
20 minutes.
Yeah, between 20 to 13 minutes. 30 minutes.
13.
Yes.
Okay.
Thank you.
Okay, there's another question up there.
Hi, Morgan from Skygeo. I wanted to ask, L-band's quite penetrative, so what kind of vegetation are you actually picking up in in these areas, and how much coverage do you expect over the whole region you're monitoring to actually see?
Oh, the whole region is vegetation. It's wetlands, so we have different type of wetlands, forested type, herbaceous type, and within those there are subtypes, but all the area is vegetated.
Yeah, but so, yes. Sorry, my question is L-band is commonly used for penetrating vegetation, and so, but here you're saying you're using it to actually monitor the double bounce between the vegetation and the water level.
Yes.
So what kind of vegetation is it possible to do this technique with? Because I'm assuming you need quite big it's not just some grasslands, it's...
Oh, yes. So that's, if I understood properly the question. So it works in different kind of vegetation, but with the L-band, it works better with forested type of vegetation or more tall vegetation. C-band would work probably better with shorter vegetation, but the problem would be the coherence loss, because herbaceous type of wetlands is more sensitive to wind. So even if we do have signal, it's going to be pretty bad signal. But the L-band shows better results with forested type of wetlands. They are pretty high, but still the penetration allows that.
Okay, thank you.
Did I answer the question?
Mostly, yes. I mean, my question was kind of some areas are going to have larger growth than others. So I'm interested how you manage the coherence loss between these areas of higher vegetation and lower vegetation.
How do we manage the coherence loss? And we don't actually manage the coherence loss. If we have bad coherence, we just, I'm sorry, maybe I misunderstood the question.
We can talk after over a coffee.
Yes, thank you.
Okay, are there any other questions?
Maybe one. Yeah, if I can just, if I understood correctly, you applied ICA to the stack of airborne images, am I correct?
Yes.
So the question is, I guess that you extracted, if the stack is 20 images, I guess that you extracted the 20 signals.
The what? Sorry?
If you apply to a stack of, I don't know, 20 images, you get as a result 20 independent signals. So
Yes,
how
at
many of
most.
them? Yeah, how many of them have a meaning point of view?
Oh yes, they all have a meaning. If your question is
Yeah.
comparing to the PCA, maybe
Yeah.
they all have meanings because, I
So
mean,
there are 20 or whatever independent signals in the stack.
we can generate up to 20 independent signals, and they will all have the same variance, but depending on that's required like a different interpretation on the sources to identify the one that we want to extract and the one that are of no use maybe. But my point is, here we had only 7 acquisition as input, so we can only generate up to 7 acquisition. And because the atmosphere is really, really variable, so we have different feature for each time step. So we kind of used all the independent component. But I believe if we have a really long time series, we can apply in PCA before, like a dimension reduction. We can use a PCA and only take the first component and then apply ICA. So using the PCA, it will determine how much component are necessary to mix the sources within. But because we have only short time series, so we generate all the time, all the independent component.
Thank you.
Thank you.
Okay, we have a few more minutes, and we shouldn't really start earlier with the next talk. If there's other questions, there's an opportunity.
I'm not sure if I understood well. You said that you are making images, one image 20 minutes after another one. Am I right? Or 50 minutes, doesn't matter, but...
Yes, it's acquisition every 20 minutes.
Yeah. And how large change of the biomass or of the water level do you expect in 20 minutes?
Oh yes, yeah. Because we are talking about coastal wetlands in Louisiana, the tides change really rapidly enough that water level can reaches, okay, let's say 20 to 30 centimeters. It can change within half an hour or 45 minutes. Yes, it's really that fast due to tide cycle. It's really fast. Yes.
Okay, thank you.
Yeah. Welcome.
So, any other questions?
That's it. Thank you. Oh, yeah.
Okay, I still have questions. So the whole campaign, okay, with the 20 minutes time difference, so the whole campaign took how long? 4 hours or something like that. Is that right?
Oh, yeah. So we had many flights during fall and during spring. And even during fall, like we have 3 days. Each day we had many flights. So this is just a sample of one footprint, one data set. But even for one footprint, we had like 3 or 4 data sets of spring and fall. And every day it was around 3 hours to 5 hours of acquisition. And yeah, we did that spring and fall, 3 days each, I think. So in general, we had 16 flies. 16 flies with that, yeah. Mostly the baseline varies between 15 minutes to 30 minutes, and the whole acquisition time was between 3 hours to 5 hours.
And so the tidal signal is probably something what you can eliminate because we know how much the tides are.
No, that's exactly what we want to do. We want to, so the idea was to do acquisition during different period of the tides, low tides, high tides, or between tides. And we wanted to retrieve the dynamics, the water dynamics through tides, to generate models, to know which part of the river delta, Mississippi River Delta, is sinking and which part it might resist to the sea level rise.
Okay, thank you very much.
Thank you.
So then we can, thank you.
Thank
Then
you.
we can go ahead with our next talk. The next presenter is my co-chair, Giovanni Nico from the CNR in Italy. And he's going to talk about digital twins of the atmosphere.
Thank you. Good afternoon to everybody. Besides me, the other two colleagues who participated to this work are Pedro and João Catalão from the University of Lisbon. And okay, the question of this talk is what we try to do to understand if the assimilation of INSAR data can help to update the numerical weather models and do it a better digital twin of the atmosphere. Move this way. Okay, this is the outline. I will shortly introduce the concept of INSAR meteorology, skipping all the part of INSAR processing, and recall the concept of a digital twin. Then I will show a few visualization tools for the analysis of output of numerical weather models, and then I will try to answer the question, which is the title of this talk, showing the result of an example. So this is the assimilation scheme that has been applied. It's one of the possible protocols that can be applied. Okay, put at the bottom a reference, but okay, there are many others. So we have we start from the acquisition time of the SAR image, which is TSAR, and then this will also set approximately the time when the output of the assimilation will be generated. Then the model is warmed up 6 hours before using a spin-up procedure, and starting from TSAR, there is a time window, and 6 hours, whatever, within which the output, the forecast, the predictions are produced. And from the mathematical point of view, it is used a cost function, JX, that consists of different, ingredients, so to speak. Y is the SAR image that is used that is assimilated into the numerical weather model, and then there is the output of the assimilation, which is X, and the XB is the background, the output of the numerical model before the assimilation. Why SAR maps should be better than other measurements that are usually provided to a numerical weather model? The reason is that precipitable water vapor maps produced using a stack of SAR interferograms are characterized by a higher spatial resolution, so they can get, better information about the spatial distribution of water vapor into the atmosphere. And the B is just a matrix that is used for studying the correlation of the solutions, which are generated different times, separated by 12 hours, and each solution is run for 24 hours. One information, sometimes which could be useful to understand when the assimilation of SAR interferograms is useful. Not always it is useful. What we observed is that when the speed of the air masses that are moving within the footprint of SAR images is relatively slow, so there is enough time to collect information about the characteristics of the moisture of this air mass that is moving within the footprint. So when this happens, the window of where the predictions are updated and somehow enhanced is longer. So there is this diagram, if I manage to, in any case, the diagram on your right, when there is a linear relationship between the transit time of the air mass and I would say the time window where the prediction are, I would say, enhanced somehow. And this is an example which is referring to the Appalachian Mountains, where a very long time series of Sentinel-1 images had been used. From the point of view of digital models, there are two different kinds of digital models. One class is related to a physical model of the phenomenon, which is the case of numerical weather models that maybe can be considered a mature digital example of digital twin. And there are other approaches which are based on data-driven algorithms like AI or whatever. We prefer the first example just because in this case there are some advantages. We don't need huge data sets, so we can have an idea about the variables which are useful for the interpretation of the phenomenon. And I would say there is a higher potential of generalization because we know what are the assumptions, which are the limits of the assumptions that have been done. So we can also understand how far we can use it to predict some event. So this is an initiative of the European Commission. We are not working in this, but it was, I'll say, our reference is Destination Earth, and the atmosphere is one of the domains of this initiative. And the need is to monitor and simulate, to develop tools to monitor and simulate the atmosphere for meteorological purposes, and to, in that case, was anticipate natural disaster that, in our understanding, is get better prediction of extreme weather events. And this is what we tried to do. So we used an example of numerical weather model, which is WRF, just because we have more experience on this numerical model, but other models can be used, like the French AROME or the German Cosmo. And we use as a data lake Sentinel-1 images, so long-time series of Sentinel-1 images that have been used to generate precipitable water vapor maps. ERA5, because ERA5 is a model that is used to set the initial and the boundary conditions of the WRF model. And the digital twin engine is the mathematical tool of the 3D VARA simulation I mentioned at the beginning of this slide, that is used to, I would say, to create replicas of the WRF model, to update, to change the values of variables of this model, and then from these updated variables try to get some prediction, for instance, of rainfall patterns or whatever, also the moisture in the atmosphere. So some visualization tool. One useful visualization tool is the concept of Lagrangian, which is a way to describe the trajectory. This is the mathematics that is used to describe, to draw these trajectories. This is an example on the left. There are 4 different trajectories. The colored dot is the starting of this movement of a given particle in the atmosphere. In this case, 18 is the time where, at the top, the title of this plot is the time where the simulation has been started, and 19 is the day, and 18 hectopascal is just setting the altitude in the atmosphere where the particle has been started to be observed. And then we have 4 different trajectories that can also on the right, it is basically the same plot that is seen from a different perspective. This is useful because we can have, a tube of trajectories that are helping us to visualize what is happening into the atmosphere. And on the right, the color is representing the specific humidity, or better, the change in the specific humidity that is generated after assimilating the numerical weather model. And this is also useful because besides the dynamic, the visualization of the dynamics into the atmosphere, it's also possible to have a look at what happens at a given place. For instance, a given point on the terrain surface with given latitude and longitude, so we can see what happens at these columns along the time. And in this case, 2 variables are observed, are shown better, the specific humidity and the temperature. So how this is, how these 2 variables are changing along the time due to the assimilation of INSAR data. And again, we can use these 2 visualization tools to study a real-life event. This was an example of extreme weather event that affected the southern Spain in Andalusia, and the paper at the bottom is describing more or less the results of this assimilation. In this case, we're using the concept of Moller diagram. The shaded figure at the bottom is the digital terrain model of that area, and what we can observe in this slide is how the water vapor mixing ratio, which is similar to the specific humidity, there is just a change in the density. We need to multiply by the density of water vapor. How this is changing along the time, and also how this quantity is distributed both in space and, let's say, latitude and longitude. And besides this, is also represented the information about the temperature. And okay, and now with these visualization tools, I can try to describe the example that we use to try to answer the question, which is the title of this. this presentation. The phenomenon is the low-level jet that is affecting South America. This is due to the winds that are blowing from the northeast part of, from let's say Guyana or northern part of Brazil, and this is pushing the air masses towards the Andes, and this is giving rise to a concentration of the moisture, which is represented in this slide. And I don't know if I managed to show the pointer. Maybe here. This is the tube, or if you want, the channel where the moisture is concentrated. These are the hands, and this is the spatial distribution of this channel. So this channel is moving along this direction towards Argentina, Uruguay, towards the sea. And this is the phenomenon that has been used to try to, in this assimilation, to try to better describe the phenomenon itself, which means the spatial distribution of the moisture. So after the assimilation, maybe I jumped something. Sorry. Okay. Okay, so what we observed is that after the assimilation of INSAR data, we observed a better concentration of the moisture within the tube, and also starting from this better concentration of the moisture, we computed also the precipitable water vapor using the numerical model and compare this with GNSS stations that have been are available in that area. And we observed also the updated prediction of rainfall patterns with the measurements of the GPM satellite. And these are a few images. So on the left there is, the geographic area, and on the right there are two examples of SAR interferograms. It's not SAR interferogram. This is already the map of precipitable water vapor. This map has been geolocated and has been also calibrated using GNSS data, and a solution of the WRF model has been used to compute the precipitable water vapor at initial time. So in this way, the differential estimates of precipitable water vapor, which are provided by SAR interferometry, have been integrated. So what we can observe is here a better visualization of the channel of the tube with the moisture where that is expected for this phenomenon. And this is a comparison with the ERA 5 product, where I'd say the visualization of the tube is not so easy, the meaning that the model is not able to reproduce this phenomenon. These are just some of the, I'd say, the positive some of the results. In some other cases, the Sentinel-1, the assimilation of Sentinel-1 data did not provide an update of the WRF, also due to the speed of the movement of the air masses within the footprint. And this is another example. In this case, this is the output of the WRF model, and this is the change, the difference in the moisture that has been estimated by the WRF model before and after the assimilation. And again, it can be visualized, the movement along the time of this moisture within the tube, so to speak, of the low-level jet. And this is, most numerical comparison of the results. In this case, the root mean square error and the bias between the moisture, the precipitable water moisture that has been computed using the output of the WRF model after the simulation and before the simulation, and the GPS measurements. And it can be observed that there is, I'd say the error is decreasing when comparing the output of the assimilation with the control, which is the WRF before the assimilation. And this is for 2 seasons of this, for 2 different times of this phenomenon, which is the warm season and the cold season, because this phenomenon is also characterized by an oscillation in time. And an enhancement has been also observed for the bias. And okay, this is a better description also of the vertical distribution of the moisture that is expected for this phenomenon, because the tube also is located. It is expected that it is located more or less between 1 and 2 kilometers in altitude. So to summarize, what we observed in this experiment is that the assimilation of INSAR data helped to help us to get a better knowledge of this of the water distribution in the atmosphere, and also give us some hints, or better, could give meteorology some hints to better model this tube, because it is possible to better represent the spatial distribution of the moisture. So the conclusions. The conclusion can be summarized in these 3 points. First, okay, even if the numerical weather models can be considered, let's say, mature digital twins of the atmosphere, there is still space for some improvements if we want to use them, I don't know, to enhance the prediction of extreme weather events. We observed that the assimilation of precipitable water vapor maps provided by Sentinel-1 could improve the weather forecasting, and also, yeah, to update the predictions of the numerical weather models. And this can support something that we can call precision meteorology, which means be able to better describe, to better predict extreme weather events. And the last point is that the assimilation of these maps can also help to update the value of variables of the numerical weather models, and this can be useful to generate synthetic data. Maybe I don't know. For instance, the synthetic precipitable water vapor, that is spatial distribution generated using the numerical weather models, or some other variables that can be used to develop some other examples of digital twin based on data-driven approaches. Okay, that's all. Thank you. I don't know if you have some questions.
Thank you very much, Giovanni. Okay, yes, questions? Felipe?
Hey, yeah. Thank you for your presentation. I was wondering, like, how often are you acquiring? What is the temporal baseline of these Sentinel-1 images? Because my question was, like, you're kind of tracking these water vapor features, and I was wondering, like, how stable in time they stay, so that you're able to say, okay, this is the same one that is just moving.
If I correctly understood your question. Okay, this is one of the points, is assembling in time. In this case, the temporal baseline is 12 days, if I remember correctly, but both ascending and descending tracks have been assimilated. But this is one of the limitation of this technique, because of course you can measure the moisture in the atmosphere just at a given time. So you have to use the difference between the two measurements to.
Okay, that answers my other question, was whether there was possible, or you were thinking on doing some kind of real-time estimation of all these atmospheric events that you are describing.
Yeah, my understanding of real time, or near real time, is the following. I introduce a given, I update, let's say, the precipitable water vapor information provided by Sentinel-1, but other satellites can be used. This is just an example now. So I can give more or less real-time predictions within a window, let's say, of 6 hours, 4 hours, depends on what I told at the beginning, how fast the air masses are moving within the footprint. So it is possible to provide these updated predictions of the WRF model just within these small windows to get better predictions of some weather event. So in this respect, can be more or less real time, but just within small windows, not in a continuum.
Okay, thank you.
Okay, are there any other questions over there, Ramon?
Yeah, thank you very much. I was wondering, you have precipitable water vapor maps, but in principle, you measure the delay, right? So we could have the integrated reflectivity. So in the integration with the weather models, is it really necessary to go to precipitable water vapor in the first instance, or can you directly assimilate the delay?
We try to do both. Actually, they are quite similar. So we tried both assimilation. And our understanding is that because precipitable water vapor is just the delay multiplied by a given constant. So it's basically
I think you have the humidity and the temperature and the pressure.
Which
right?
can change, but we use just one constant for a given area.
But so in the assimilation, it's possible to directly have the integrated effect in there. Yeah. Thank you.
Okay, any other questions? If not, then let's thank our speaker again, and let's move on to the next speaker. That is Jihong Liu from KAUST in Saudi Arabia. And he's going to talk about intratropospheric delay modeling. Okay, the floor is yours.
Okay. Thanks for your coming. My name is Ji Hong. Today my topic is about intratropospheric delay modeling based on its spatial temporal characteristics. Actually, my topic is mainly for INSAR deformation monitoring. So for intratropospheric delay correction. Sorry. Okay, as we know, INSAR interferograms contain not only displacement as well as atmospheric delay, orbit error, or decorrelations noises. Among these, if we want to get accurate INSAR displacement, we should first correct these errors. Among them, the atmospheric delay is the most difficult component to correct. So nowadays, one of the most common methods is to use the independent data set, like weather models or GPS, then interpolation with these weather models to get the INSAR atmospheric delays. And however, due to their inconsistency of the spatial temporal resolution, or in some locations, there are no sufficient observations. So sometimes if we correctly use this kind of method, the result will get even worse after correction. And also there is another kind of method, I call it data-driven method. They just use the correlation. For example, it's the correlation between the DM and the stratified delay, then correct this kind of component. And another kind of use the temporal random characteristic of the turbulent delay to correct the atmospheric delay. However, due to the existence of each error component, and we generally correct one kind of errors independently. So the existence of other kind of errors will affect the correction in performance. And also there is no mathematical models for the atmospheric delay based only on the INSAR data. So my method is about aims to model the INSAR tropospheric delay and at the same time as well as the orbit error. However, from this equation we can see if we want to correct the errors, this is just a U-post problem. So my solution is to incorporate their spatial temporal characteristics as additional constraints to make this equation can be solved. So first, as for the deformations, I consider it is correlated both in spatial and temporal domain. of course, in the temporal domain, we can, this kind of correlation is not included like the earthquakes. There are suddenly jump for the deformation. And for the stratified delay, they are generally correlated with the local DM. And in a small zone, we can generally fit it with a linear model with the DM. So we call this kind of component like the DM correlated component. And the following, as for the turbulent delay and the orbit error, these two components have different spatial characteristics in a large area. But if we zoom in a small window, as we can see, they can be fitted by a position-dependent ramp. So I call these two components in a small window as the trained component. Sorry. Oh, here. Oh, as the trained component. So in the following, so my proposed detrained INSAR method is to decrease both the trained and the DM related component in INSAR time series. And the input is the time series with deformations and errors, and the output is the corrected deformation time series. And we should first establish equations for each pixel at each time based on the pre-array information. And we get a larger equation detrained INSAR model, then use the least square to solve the unknowns. So this is the larger detrained INSAR model, and the unknowns include deformation, trained, and DM related components. And the key is how to establish each equations for here. So in the following, I will introduce how to establish these equations. First, in a small spatial window, the INSAR observations can be divided into deformations, trained component, and DM related component. And first, if we, based on the full information of the trained component, we can get an equation like here, in which the trained component can be modeled as a position-dependent ramp. And second, based on the DM correlated component, the similar, we modeled the DM related component as a linear model with the DM. And after the spatial domain, in the temporal domain, just like for example, in 3 or 4 months, we can consider the temporal deformation as third order polynomials. And we can use this a priori information as constraints in the modeling. And constraint, the formula of the constraint just like 0 equals C multiply X. X is the unknowns, is the deformation time series, and C is the coefficients. How to determine the C? We just follow the rules like 0 equals the fitted deformation at the time, and the original deformation at the time. The differences between these two components is 0. So by this rule, we determine this constraints formula. And we also add another constraint like the non-deformation pixel. As we know, INSAR deformation, we generally need an unwrapping reference, like in the far field or in some non-deformation area, like GPS or something else. So if we have this a priori information, we can also model as a constraint, like the equations. So after this for a priori information, we can combine all these informations and establish the equations for each pixel at each time. Then we finally get the detrained INSAR model L equals Bx. And we use this square method to solve the trend and DM-related components, then finally get the displacement. Okay, after proposing a new method, we will first simulate the data to validate the performance. First, we simulated the deformations and the orbit errors and the turbulence, and as well as the stratified delays, and sum all these components, we get the final simulated insert data set for correction. And for comparison, we also include two benchmark methods. The first is we call it a fit filter method. That means just fit ramp and DM correlated components in the spatial domain. Then use a temporal filter in the temporal domain. And another method is the common scene staking method. Sorry. Here is the comparison between different methods. First, the first row is the fit filter correction result, and the second row is the residuals. And these two rows is the common scene staking method result. And here is our proposed detrained insert method. As we can see, our method have small residuals and more clear deformation time series. And also, we use the 2021 Madu earthquake as the real data case studies to validate. And here is the cosseismic three-dimensional deformations. It's a left lateral strike slip events. And we use 16 months of Sentinel-1 images for the deformation monitoring. And here is the uncorrected accumulated deformations for ascending and descending orbits. And here, for the real case study, we also involve the independent data set, like the Gagos and the ICAMS for comparison. Here is the result. And also, we use the data-to-data-driven method, fit filter and CSS for comparison. And the last is our detrained insert method. As we can see, our method can get more clear result for the post-seismic deformations. And there are also several GNSS data for validation. Here is 4 examples. As we can see, for example, for the first GPS result, in the first several days, the deformation variations, our result can clearly capture this variation. The red dot is our detrained insert result. And here is the RMSEs by comparing with the GNSS data. As we can see, our method can get the smallest RMSEs. And also, here is an interesting event that occurred in the August, 3 months later of the earthquake. There is a small event here. And our method can clearly capture this small event deformations. However, for the fit filter and CSS method, the fit filter, there are some severe atmosphere delays here, and we can't clearly identify the event deformation. As for the CSS result, since they have a temporal filter, so the cosseismic deformation of this event will be distributed in the near acquisitions. As for the independent data, due to their limited observations, it can hardly capture this small event. And we also show the temporal deformations of 4 points here. As we can see, the red dots, our method can clearly capture the deformations and the accretions of these small events. And here is another example about the Turkey earthquake. Here, the original data is from Kanwan at UC Berkeley. And this is the 6 months post-seismic Sentinel-1 data. And our detrance INSAR method can clearly correct the atmospheric delay as well as other errors and make the deformation much clearer. And here is another example is near the Dead Sea. And this Dead Sea, the water level decrease induced the rebound of the ground. And figure A is the before correction, and figure B is after the detraining INSAR correction. As we can see, our method can make the deformation much clearer. And here is also a GPS data. GPS station is here. And we compare with the temporal filter method. The green dot is the temporal filter result. As we can see, there are very obvious annual variations of the deformations. However, due to some variations of the original data in 2016, in the year 2016, and the filter method, the green dot, counter captures the annual variation in this year. However, in our method, the blue triangles, although there are two acquisitions have deviations from the GPS data, but the overall the temporal pattern is consistent with the GPS data. So this is also validates the performance of our method. And we also open our detrained INSAR code. The input is very simple, just the displacement time series and the data list as well as the DM of the study area. And there are also several key parameters can be set for different case studies. And the output is just the corrected data time series. And the advantage is simple input and flexible to adjust the parameters. So why not have a try here? So finally, conclusion. We propose here a detrained INSAR method for correction the atmospheric delay. And we conduct simulation and real data for validation. And the detrained INSAR code is open. And I think INSAR atmospheric delay is still a challenging topic. I just want to contribute a little for this topic. And to be honest, the detrained INSAR I can't say is the best, but at least in some cases it works. And also there is other advertisement, and I have another topic, another presentation about the all-fault deformation of the Turkey earthquake from 3D displacement, and they are also open code to share. Okay, thanks for your attention.
Okay, thank you very much. I'm sure there are questions. Yes, Fabien.
Yeah, thank you for your talk. I was wondering, so if I understand correctly, you are looking on Windows, on local Windows, to calculate the correlation, the stratify and all. Do you have a recommendation on the Windows side that we should use on especially volcanoes if we have stratify signal that might be also correlated with topography? Do you have an idea of the best kind of window size to use in this case?
The window size, I prefer to use like the 1 to 2 kilometers for the window size, the spatial window size.
Okay.
Here I didn't consider using the special variable window size because just maybe I can improve the window size in the future, but
It's
not
fixed right now.
Yes,
Yeah.
just fix the window size.
Okay.
Thank you. Thank you for your question.
Yes, here's a question, David.
Yes, if you have GPS data in the region, can you incorporate that into this whole structure?
Yes, I can. In the model, I have the setting for incorporating the GPS data, just like input to assist the model. Okay, thank you.
I also have a question. I have two questions actually. The code, Python or something else, and the other question is the images what you showed, the comparison after your correction and before the correction. Before the correction was without any tropospheric correction, or?
Okay, the before correction is no atmospheric correction, just the original. And the code format is using MATLAB, just MATLAB, some MATLAB code scripts, yes.
Okay, thank you.
Thank you.
Any other questions? If not, then this concludes this session, and
Okay,
let's run to the coffee before the other group goes.